Okay, we got unit 13, electricity. This is our last unit here for second semester study guide. Start with some equations. F equals K, little charge, big charge, d squared. That's called Coulomb's law. The units for that will be newtons as you're solving for force. Go through some of the different things that can happen. Positive and positive, they will repel. Positive, negative would attract. Negative, negative, repel. Rub two objects together, one becomes positive, one becomes negative. This is what we call electrostatics. If we look at A and charges A and B, and A experiences 3 force towards B, that means B experiences 3 newtons towards A. The charges must be different if they're going toward each other, just like we saw to the left. We can now do an example electrostatic problem. So our example is a -3 and a -8. So they're both going to push equally. Notice that I'm making the arrows the same size because they push equally. However, it takes 2 charges to make this force. So when I want to find the force here and here, I can do that by taking K, Q divided by d squared. So I get 99 times the charge, 3e negative 6 times this charge, 8e negative 6. Notice I'm putting it in as absolute value. I can just look at a picture and see my direction. I don't need to worry about direction. The direction or sign isn't going to affect that as far as our math is concerned. And the distance between 0.5, remember you got to square the distance. So when we set all this up and we plug it in, we get 0.864 for how many newtons. And then we'd also label that as away. When it comes time to punch these things in, you want to do 99. Oops. 9 second comma 9. That's how you do the constant times 3e negative 6 times 8e negative 6 divided by the distance between 0.5 squared, and we get the same number that I just wrote down, 0.864. So that's electrostatics. Notice there are 6 problem sets you'll want to look at to study for electricity. Should be the most recent thing we did, so it should be pretty well ingrained in your brain. Go on to the next one. Electric field is equal to the K constant times the source charge divided by the distance squared. Electric field line rules. They never cross. Positive to negative. Closer, stronger. There is a 4th rule, and that's electric field is always tangent to the field line. Charge of a proton, also known as a test charge. Oh, by the way, this is newtons per coulomb. It's a force field ratio of force per charge. Charge of a proton, 1.6 e negative 19 coulombs. That's our test charge. We're going to use that here in this problem. So here's our example electric field problem. So we have a charge in space. The field lines are going toward because it's positive 2 negative. Oh, away, I mean. I lied. Away. Away. So they go away. And then we're going to slap down a proton right here at x marks the spot. So we'll have to use that same equation that we wrote out earlier on the left side. So what we do is we say 99, which is K, times Q. Just make sure you can see the equation. Times Q. Q is the source charge, so that's 2e negative 6. And we have the distance between 0.01, and we square that distance. That's in meters. That'll help me figure out what the electric field is. So 9e9 times 2e negative 6 microcoulombs divided by 0.01 squared is this huge number, 1.8 e to the 8th newton per coulombs. This is typical for electric fields. You could expect these to be big numbers. Hardly any room to write this. Then we got to find the force on a proton. So now we're going to slap a proton down at x marks the spot. Force is equal to the test charge, little q, times the electric field, which is what we just found. So I'll put in 1.6 e negative 19, which is the charge of a proton, times 1.8 e to the 8th. And we get our force, 1.6 e negative 19 times 1.8 e to the 8, and I get 2.88 e to the negative 11, which is typical for this. It's pretty small for your force, 2.8 e negative 11. So that's an example of electric field. Take a look at circuits now. So there's parallel and series. Parallel has the same voltage. Series has the same current. Conventional current always goes from positive to negative. Look at some of our equations. Effective resistance in parallel is R1 times R2 divided by R1 plus R2. Ohm's law is V. In series, the effective resistance is R1 plus R2 plus R3 plus etc. plus however many resistors you have. Power is PIV, current times voltage. Get down into our units. A volt, same thing as saying joule per coulomb. An amp, coulombs per second. A watt, joules per second. Let's do this first thing. If you have a current of 2 amps electrons per second that pass, how many electrons per second pass through the circuit? So 2 amps. Go over here to our equivalency. Amps are coulombs per second. So we say 2 coulombs per second. If you have a current of 2 amps, how many electrons per second pass through the circuit? So every 1 second we have 2 coulombs of charge. Remember, 1 electron is the same as 1.6 e negative 19 coulombs. The coulombs cancel and I'm left with electrons per second. So what ends up happening is we just divide whatever the current is, in this case 2, by the charge of an electron, 1.6 e negative 19. Oh, let me do that again, I forgot to make it negative. 1.25 e to the 19. Electrons per second. So we come over here, 1.25 e to the negative 19 electrons per second. We got a little circuit problem going here. Looks like combination, series, parallel. Lots of Ohm's law going on here. The series part of the circuit has 5, 3 plus 2. The parallel part has 4 times 1 divided by 4 plus 1. 4/5, 0.8 plus the 5.8 ohms is the effective resistance of the parallel part, 5.8. Current in the battery. Use the effective resistance and the voltage created by the battery and do Ohm's law the first time. Define the current going through the battery and everything in series. So Ohm's law looks like this. Put in 5.8 for my resistance. Put in 6, the voltage of the battery, and solve for I. Get almost 1, a little bit less. 6 divided by 5.8, sorry, a little bit more, 1.03 amps. So where has 1.03? Everything in series. So like for example the battery, 1.03. The 2 ohm resistor, the 3 ohm resistor. That 1.3 is going to be divided up amongst the 4 and the 1. Most of the current will go through the 1 because it has less resistance. Some will go through the 4, but most of it will go through the 1. We'll just go ahead and deal with some of the things like voltage here. So we got V equals IR. I can put in 1.03, put in 3, put in 2, see what I get for my voltages. So I get 3.09 and then 2.06. So that's how I get these things. Now remember, if we add up all the voltages when we're done, it should equal the voltage of the battery. But you only add up 1 voltage for the parallel part. So now we're going to do Ohm's law again. But this time we're after the voltage in the parallel part. So I put the current that comes into the parallel part right here at the break. I had 1.03 amps. I put in the resistance of the parallel part, which was 4/5. And that'll tell me the voltage of both the 4 and the 1, or the voltage at the break, how much push I have at the break. So when I do this, I get 0.824. So 0.824 where? 0.824 volts here, 0.824 volts here at the top. They both have the same volts, parallel, same voltage. Okay, so now I have to find out how much current. Ohm's law yet again. We'll do the bottom one first because it's very easy. Put in 0.824 and 1, and I get 0.824 for my current. That's most of the current. I can also do Ohm's law. I can put in 0.824 and I can put in 4, and I can find out how much current goes through the other one. 0.206. 0.206 plus 0.2824 equals 1.03. When I'm done, I can kind of check it by taking 2.06 plus 3.09, 0.824 should give me 6. Can't have more voltage than the battery creates. 5.97. It's pretty close to 6. Looks like I was supposed to write the current in the battery down here. Whoops. Alright, so then just a few more things. Magnetism, how does it change? We go from north to south. Field lines never cross. Closer, stronger. One more thing. Magnetic field lines are always tangent. Magnetic field's always tangent to the field line. We've got our last equation here, which is QVB. Charge, voltage, magnetic field. These things then associate with your hand to find direction. Force is your thumb. Movement of charge or velocity is the index finger. And then your magnetic field is going to be your middle finger here. So that's all 3 parts of this law right over here. Alright, that's about it. I think we got them all now.